a linear operator is also a linear operator. All right. So in fact, the inverse Laplace transform also has this linearity property. Yay. Even though it's not actually an inverse. Anyway, sorry, I said something. Yes, whatever. Not actually an inverse, but yes. I digress. I mean, you can fuss about whether or not this is actually an inverse. If you think about it, it can't be an inverse because this integration doesn't pick up functions which differ by a couple points. Right? If I take a function, I put a hole in the graph, and I take the value and make it 10 rather than 2, that doesn't change the integral. So when I take the inverse Laplace transform, how do I pick out the function which had the hole in the graph versus the function which is continuous? I can't tell the difference. So the inverse Laplace transform, usually by default, is the like continuous function which takes that integral. But although that's too strong. Anyway, there's an I mean, if you're a math person and you start thinking about, is this really an inverse transformation, you can get confused. I should shut up. All right, so what is this? Don't be confused. Tell me what it is. What is the inverse Laplace transform of 1 over s squared plus 1? Right, 6 sine t. And this. And there you go. That is the solution to the initial value problem. You can check, right? It's y of 0, 1. Yep. Is y prime of 0, 6? Mm-hmm. Mm-hmm. Kind of neat, huh? I think it's kind of neat. Let's go looking for trouble. Sure. Example 5. Let us try to solve y prime prime plus 2y prime plus y, right, equal to, I'll make that a minus 2y prime. Woohoo. E to the t. And to keep life relatively friendly, we'll let y prime of 0 equals to 1, but y of 0 will be 0. Solve. So why is this going to be unpleasant? You guys have worked a few problems. You should know what's ahead of us. What's the homogeneous solutions to this problem? This is lambda equals to 1 repeated, so the homogeneous solutions are e to the t and t e to the t. And I just put e to the t as the forcing term. Not cool, right? So this should be unpleasant. So here we go, Laplace transform. This would give us s squared big Y. And then I have to take account for initial conditions. Minus y prime of 0 gives me minus 1. Plus 2s times big Y. Minus y of 0, but y of 0 is 0. No contribution there. Plus big Y. And then the Laplace transform of e to the t. What's the Laplace transform of e to the t? It's 1 over s minus 1. So I solve for big Y. It's 1 over s minus 1 times s squared minus s squared plus 2s. I'm sorry, I can't do math. You guys, there's an error I made here, which is a significant one. See this? That is supposed to be a minus. All right. Plus 1. And I also have plus, what is this? 1 over s squared minus 2s plus 1. Yeah. This piece is fine. It's kind of already in its nicest possible arrangement. But what we're looking at here is, in fact, this is actually, oh man, son of a gun. This is actually not bad at all. Oh, I wanted this, you know, I go trying to make trouble and it just works out nice. This is very disappointing to me. I'm going to have to end class early. Dang it. This is just miserable. Those are nice because those are already, I mean, you got to think about the one thing we didn't derive, which was the Laplace transform of, what was it? E to the at, t to the n is what? N factorial over s minus a to the n plus 1, right? So we need to kind of undo this. This says that the inverse Laplace transform of 1 over s minus a to the n plus 1 is what? It's 1 over n factorial, right? Times e to the at times, that's t to the n, obviously. Look at that, I made a t sub n. Great, good job. T to the n. I don't know what t sub n would be here. Just crazy. All right. That is all we need. I mean, this is essentially on the table. I might add it to the table if it's not there already, because we need it sometimes. Like this one, we need it. So inverse Laplace transform, what do we get? Y of t equal to n. This is n equals to 2, right? This is n equals to 1. Because we're looking for n plus 1, right? So I got 1/2, and a is equal to what? A is 1 in both cases, right? So I have 1/2 e to the t times t squared plus t to the t. Well, I guess I've written e to the tt. Let me rewrite this. Y equals to 1/2 t squared e to the t plus t e to the t. There's your solution. Initial values already met. Now, certainly, we already have a method to work this problem, right? An annihilator method, guided undetermined coefficients. But I think this method is kind of computationally comparable, right? I mean, this is another way to do it, which is not really, it might be easier, it might be harder. I mean, it's kind of on the bubble of whether or not this is easier or harder than our previous method. I don't know. Disappointing. I was wanting this to be more ugly. But anyway, oh well. My intention was to show you the need for partial fractions with this example. I have failed. But the partial fractions came up organically in my motivating example. We need to talk more about partial fractions because to actually calculate inverse Laplace transforms, you need to be able to write your function as a sum of things which you can take inverse transforms of, right? So if I've got something like 3s plus 7, it's plus 7, over s squared times s squared plus 3s plus 2, that's lovely, but you can look on this sheet all day long and you'll never find the inverse transform of this, right? But if you rewrite this as like a over s plus b over s squared plus c over s plus 2 plus d over s plus 1, well, then you're in business. All of these have inverse transforms, and that's what partial fractions is about. it's an important algebraic issue we have to deal with more in here. I'll try to work a few examples of that next time. If you don't want to wait for me, read the section on inverse Laplace transforms in your text, or look at my notes if you like, or whatever. Anyway, see you guys. Oh, homework. Do turn your homework in. If you'd like to turn in next class, 10% deduction. If you'd like to